So we'll wait for Hamida.
Yeah, she. Okay. I don't know where she is.
Okay.
Just to see if you can see her.
So let's start. People will come after. But I prefer that we start with the time.
Yeah.
So welcome for the seminar today. Thank you for coming. So I am happy to present to you Dr. Radislav Poterioli from General Electric Villanova Advanced Research Center. And he's also the industrial distinguished lecturer of the IEEE sensor concept. So today, Radislav will present to us the impact of materials, transducers, and contemporary multivariate analytical design of next generation gas and biological sensors. Please, Radislav, the stage is yours.
Thank you, Hamida, and thank you for having me here. And good morning, everybody. So I'll show you some of our results in this lecture, and those photos are related to our technologies or sensor systems that we have commercialized first, and then some of the examples are not commercialized. Some of them are biological sensors and photonic sensors and RF sensors in general. But I'm happy that I have this opportunity to talk to you as a part of the distinguished lecture presentation. And the Sensor Council was formed in 1999. It has a lot of impact to our communities, and we have flagship sensors conference that happens across the world. We also have many member societies, as you can see, 26 of those, very nice number of section chapters and student branch chapters. We also have not only the flagship conference, IEEE sensors, but also the more focused conferences on different aspects of instrumentation. So IEEE Sensors Journal is a well-known first journal, first publication platform, and then you can see there are many other publications and journals happening, and also very nice newsletter. So if you look on globe of this planet, then there is USA somewhere, and the USA has the East Coast, and somewhere is the West Coast, and we are on the East Coast. So we are 3 hours from New York. We are this spot, okay? Then about 3 hours from Montreal, and about 7 hours from Toronto. So we are in that area. GE used to have a one GE logo. Now there are 3 independent companies. One of them is GE Vernova, stands for the new green energy. Then there is GE Aerospace and GE Healthcare. Okay, so from GE Vernova perspective, we are focusing on different aspects of energy of the future, and it's related to power, wind, electrification, digital, and our research center is working with all these verticals in our company. So I'm highlighting here one of the topics that we're working at GE Vernova Research Center, and you can see I'm highlighting that sensor systems development that we are developing for our GE Vernova customers and also other customers as well. So because these are the things to make the assets more healthy and having the predictive ability of their state. By assets, I'm talking about industrial assets, or it can be somebody's home, it can be somebody's car, it can be somebody's health in the field. It's really this terminology that I use. So being an industrial scientist, we also work with a lot of customers, and these days, all of them say, show me peer-reviewed opinion of somebody that you use the word sensor. And this is something that is, I've heard this today 10 times, okay, because I'm meeting with all possible sensor people. So that's why we summarize our results in different patents and publications. These are some of the covers that we had. And also we are commercializing them with our partners. So you're probably familiar with these two Gaussian curves that are shifted, okay? And you're probably familiar with one of two ways of calling these two Gaussian curves. So in the middle, there is the valley of death. Okay, so now you need to remember that these are the two mountains of opportunity. Okay, there is no valley of death, okay, anymore. Okay, and that's the quote from our PE director. So the reason that I like that quote, and that's what we practice, is that in the beginning, we engage the people who later will tell us how exactly that sensor should look like. Not now, I respect your opinion, but I'm, early development, okay? So, and then little by little, we're getting them more and more involved and things like that, okay? So more and more involved, it means that at some point, they should stop thinking about all kinds of stuff, and they need to say, this is must have, and this is nice to have. And there will be a guiding light for us to understand what are the specifications, because we are, as engineers or industrial scientists or scientists in general, once we start a sensor and it's RF, okay, to switch it to something else, like to optical, okay, let's decide it earlier than 2 years into the project. Make sense? So that's a very important aspect, and there are many nuances to that. So in my talk, I will show you two different types of our work. So one work will be on the gas sensors, and then you will see what are the learnings that we are applying for biological sensors as well. So you will see that it's important thing to know what is the existing state of the art, okay? And then you will see why we're using the word multivariable, because it means more than one output in a sensor, okay? And I'm calling it as a next generation. And then you will see how we're applying mathematics of big, very famous traditional instruments to here. And I hope it will be it's inspiring to you to understand that there is a big reason for that. In sensors community, 3S parameters such as selectivity, sensitivity, and stability are the things that people are focusing to improve to that point where more and more customers will like it. Okay, so customers is a punchline for this, and customers can be editors of science journal because they've seen so many sensor papers, okay, and they need to like your sensor paper. then you can see that we have different anticipated, in my opinion, and non-anticipated benefits. So we'll discuss those. And this philosophy, I will show you briefly how we are applying it to biosensing. So before we start into the many slides, terminology is a very important thing. And when I was in early career scientist last century, I was, debating not to the death, but intensively. Okay, why? I don't know. But basically, in this definition, okay, a sensor, yes, a biosensor is a miniature device, okay, and it recognizes something in the environment in real time, okay? And roughly it's a change in concentration of one analyte or more than one, okay, and it converts this information into a useful signal. It can be maybe digital readout, analog readout, some number of concentration after calibration. So it's a useful signal. So what I see in literature is there are two descriptions of the same word, sensitivity. I'm an analytical chemist. To me, sensitivity is what? It's a slope. Okay, no discussion. Okay, and then the ACS journal editor says in a nice editorial that people, there is another community where it's another community. Don't fight with them. And that community says sensitivity is a smallest concentration. Okay, so we know that, and we live in peace and stuff like that. So the reason that I'm showing you this correlation plot is that to impress the different customers, you show the performance of the benchmark instrument. It can be glucose blood analyzer or some EPA machine for gas measurements, and the sensor that we're developing. And then if the correlation is very nice means all these data points fit onto one line with the slope of 1, okay, then it's a very impressive from customer perspective correlation plot, okay? So my opinion is, useless. Okay, not useless, but and then there are marginal and pure correlations, and that's where the customer says, well, 0.1 R squared, I really don't like it, go away. 0.5, go away. 0.85, well, stay. Can you improve it to 0.9? So it's really something that they would like to bet their, budget or reputation or different legal actions on what is that new sensor shows them, okay? And that's why we're developing different types of sensors with more than one output, because we're inducing on purpose different independent variables. And you can see that there are different synonyms for the word multivariable sensor in literature, okay? So the reason that I'm showing you this slide again is that there is another community where the word sensor means a molecule. No fight. It's a molecule. It's a biomolecule. So that's one distinction. Another distinction is that that sensor can be actually a glass slide. I'm a source substrate. I'm a SPR substrate. I call it a sensor. Look at my Nature Communications paper. It's a sensor. Okay, I'm not fighting. And I can call it coupon because it's my slide. I can call it anything, but it's a chip. Okay, and then because it's a chip that you need to have a confocal or whatever widget to do the readout, then I'm calling it periodic readout. Okay, but from the impact to the society, it's important to understand what this type of new chip replaces, and it replaces maybe or likely very labor-intensive multi-step sample preparation and measurement and staining and all kinds of stuff. Okay, so that's a good progress in biosensing. So today is 2024. Okay, it's November 29. Or awesome. Some time ago, before me and before all of you people, there were no sensors. Okay, and you can see two examples where the first example was, hey, if we will train those, then we will do all kinds of different detection of different smells for many reasons, okay? And so that's one example, okay? And you can see from 1899, okay? So by law, in order to save the industrial workers like these guys in underground mines from carbon monoxide, by law, you need to protect them by having canary birds. End of discussion. For air bars, you have more than one bird in a cage. The good thing is that after exposure, the birds are getting back to life. So they're not like single-use dosimeters, okay? So that's something that was very exciting. And the other photo that I have is in color from 1986 from UK. That's where the year when these birds were banned, because finally there were sensors, okay? So I was born before that. Anywho, so these days, we have mobile devices, and those mobile devices have these and many more sensors, okay? Why? Because they make these mobile devices very useful for this and this, for all kinds of useful things, besides being a phone, okay? What I'm saying here is that their performance capabilities, accuracy, and everything else are so nice that in the view of customers, that each of them sold in billions of units annually, okay? So our sensors are a little far from that, but it's a very important inspiration for us, okay? And if we look at the gas sensing needs, then just a little bit of different types of gases for different applications, different industries here, and from end users, not from the sensor developments, but from the end users, you can see that they're saying accuracy is number one, and if the accuracy is good enough, I will order millions or zillions of units a year, and then of course cost will be little and so forth, okay? So there is a concept of trillions of sensors universe, and in that universe, the sensors are 17 cents each, okay? So these days, some of the manufacturers from the previous slide, they complain because their sensor is less than $1, because if they need to make more money and they are dropping the cost and they're selling them in billions of units, they need to come up with some other nice ideas. So you can see that these 3S requirements, if we're meeting them, then these are the billions of dollars of market opportunities that are awaiting for us if we show that we can, perform well, okay? So couple of examples where exquisite detection of different gases is important from the usefulness perspective is, for example, breath analysis, okay? And it can be different types of body fluids, volatiles and stuff like that. So in the scale breath of a human, there are not this list, but many types of families of volatiles, depending on the device that you use. If you use the poor man's GC or undergraduate GC, then there will be maybe 100 compounds. If you use better and better machine, then you will see 1,000 and even more than that, okay? And some of them are related to different disease states, okay? This is the table. And what is important is that in the breath, those biomarkers, because they are metabolic products and biomarkers, that's why. In the health of a healthy human, those things are not zero, okay? And that's why our goal is to differentiate between that concentration and higher concentration, elevated concentration, when there is some disease or instead of the disease present. So the reason that I'm showing this nice images, in my opinion, because they are produced by hyphenated instruments, traditional analytical instruments, and that's the gas chromatography hyphenated twice, so with 2 orthogonal responses. This one is 2GC channels and also mass spectrometry readout. So you can see that this is the signature of breath with many spikes. Okay, yes, of course, because I just told you. And in order to differentiate between them, you don't need all of them, but you want to find the one that is related to the biomarker or biomarker. And so that's why high resolution machines are very important. Okay, so if you have $500,000, it's not enough. Keep on saving. Okay, and in return, people really say, okay, now I can do this measurement. Okay, so another example on this slide is that on our smart devices, if the air quality is good, we don't pay attention to the green color. If the air quality is getting more and more into the dark red, then we see what's going on. And what it means is that if I have a kid that is with asthma or some other things, okay, I don't want that person to go there and get, to the hospital later. So I really need to have this quality of data that will help me to prevent all kinds of things that I don't want to happen. So in ambient outdoor air, these colors are related to 5 parameters. One of them is the concentrations of particles, and 4 are these different gases, as you can see. So you can also imagine that in ambient air, there are many, many, many more. Okay, but in order to make sure that the health is good and no bad things, these are there for gases. So I'm showing these types of traditional analytical equipment because these ones are approved to do the measurements with the accuracy that is actionable and useful, and World Health Organization, EPA in USA, and many others, they are really focusing on the quality of those measurements, okay? And quality comes with the cost and with the maintenance and with logistics, but, well, that's 2024 today, okay? So in sensors, there are 2 broad categories. So one category is that we'll measure the intrinsic property of a gas, okay? Intrinsic property can be absorption of a gas, maybe in the visible spectral range, or maybe in the UV, or maybe in the infrared, okay? It can be some other effects, paramagnetic and other type of things. And there are many nice technologies, as you can see from the most recent literature. And those gases are for detection. I call them lucky because they have high enough cross sections and high enough intrinsic property changes if the concentration is changing. And that's why having the sensors in the micro formats is appropriate for those gases, okay? And some gases are less lucky because if the cross section of absorption is much smaller, then you need a very large path length or all kinds of other things that become not attractive to be a micro device. So that's the reason for that first category of gas detectors. Okay, so the second category is material-based, and I'm not saying what is better. What I'm saying is that they exist in peace all the time. Okay, and the conventional material-based sensors, they're based on the fact that you have something in the air, and you want to detect that something in the air, and you have a sensing material that will respond to that gas, okay? In order to make sense of what that sensing material was doing, you need to have a physical transducer that will convert that material change into the useful analytical signal. So you can see examples of the sensing materials, and also you see examples of 3 out of 5 transaction principles in sensing in general, okay? So for gas sensors, electrical transaction principle and examples can be resistors, capacitors, some resonators, mechanical energy type, okay? So they can be different types of micro mechanical systems like accelerometers, so devices, and so on, and optical or radiant sensors, okay? The other ones that are less famous in the gas sensing will be the magnetic energy and the thermal energy for material-based sensors. Thermal energy is applied in direct sensors, for example, for measurements of thermal conductivity of different gases. So by design, by that definition, the sensor is reversibly responding to a presence of a gas, and that's why I'm showing here that reversibly means that in the presence of no gas, it will be background from the blank, and then in the presence of higher concentration and higher and so on, the responses will increase or will change proportionally, but when the concentration goes back, the signal of that sensor goes back because I'm a reversible sensor. I'm not a dosimeter, okay? So you remember that photo with the bird, and that's how the inventions were to save those industrial workers by creating different types of electrochemical sensors for preventing the different types of explosions. There were metal oxide semiconducting resistors, and you can see those patterns go back to 1970s. That's where there were a lot of lives saved. Okay, many lives. Why? Because when you have such a sensor, okay, then you do some useful actions. Okay, so to save lives, you detect concentrations that are dangerous for that. Okay, and what it means is that those concentrations are not small. Those concentrations are big, and that's my cartoon. So in the presence of known gases and big concentrations, big enough to do the actions, then those single output sensors are very useful, very good, awesome. They save lives. That's what matters. Okay. So over time, they became smaller and smaller, less and less power. Okay. Over time, the electrochemical sensors also got smaller. Very nice. But philosophically, they are designed to detect relatively high concentrations in the presence of whatever else that is not affecting your response. Okay, so that's the punchline, and that's why if those design principles stay, then if we or I dream about different types of other uses, then it becomes something that I need to think twice. Okay, so here I'm showing on this slide that if we have the high concentration of the gas that we want to detect, okay, then in the data sheets of commercial analytical or commercial sensors, they say, hey, look at my table, okay, look at my data sheet, because I'm calibrated for one gas, but I will be responding to other gases as well, not with the same intensity, maybe higher, okay, but I will respond to those. Why? Because in order to be reversible, my interaction forces are not strong, so I will maybe respond to other things. And those data sheets are saying very clearly that I will respond to many things, okay? So if we look at the examples of different research sensing materials, then you can see that these bar graphs are not with one peak, okay? So that's something to keep in mind. And then if we bring these sensors to detection of very small concentrations of those volatiles in the ambient air, those ozone, carbon monoxide, nitrogen dioxide, sulfur dioxide from a couple of slides ago, okay? Then, because for health reasons, you need to detect small concentrations. Then that small concentration becomes comparable with all kinds of other stuff, okay? And when it's comparable with all kinds of other stuff, and I'm single output sensor, then these are my correlation plots, and EPA and other people are saying, okay, so it's better not to have wrong data than to not to have data at all, rather than to have data. And then you see many other quotes, and things don't change because single output, that's what it was designed for, to detect high concentrations. I'm not using the word limitation or whatever, because it's design feature that was used for other reasons, okay? So I have many inspirations, Okay, and I'll show you two here. So one inspiration is that this is the photo that I took in Las Vegas early this year at Consumer Electronics Show, and it's amazing, not amazing, it's humongous show, okay, with many buildings. There are a bunch of buses that move these people, and they look for the TVs and for, smart fabrics, whatever. Awesome. When people come from the bus, they're sniffed. Why? Because. Okay, end of discussion. And they're very friendly, the handlers, and they can take pictures. These are photos that they took, and they're very, not cute, but they're useful. Okay, and then I was surprised that there are different services, either for homeland security or for the agricultural things or for the cancer sniffing. Most recently, I saw, oh my God, services for sniffing the bed bugs in hotels. Okay, why? Because my sensors that I've been developing when I was at grad school, well, they didn't make it. Okay, so they trained the dogs, and these are very cute things, animals, and each of them to be trained, it's only $80,000, maybe 70 if you will train them bunch, but it's not free. And they're getting tired very quickly, about 20 minutes or so. So they need, rest and stuff. So you have a small army of them. And very importantly, you must have a handler who will, gently say what to do. Okay. So that handler doesn't sniff, but it's really a team work. So this is 2024. So I think we need to think how to change the status quo. Okay. So my second inspiration is that traditional analytical instruments for what I showed you for breath analysis and for homeland security and also for ambient outdoor air and so forth, for indoor air. So these are some nice examples, non-limiting examples, but they're so impactful to the society that you can see not one, not two, but 3 Nobel Prizes were awarded for different aspects of these analytical system designs. Okay, so they're not afraid of complex chemical mixes, and they push the responses into different directions of their multivariable response. And these two photos I'm showing just to highlight that if you want those accurate results, then you will have a SUV, because you want a cavity ring down spectroscopy machine. Okay, and if you have $50,000 plus SUV, you're good. You can map the pollution on the streets. Okay, now if you want other type of measurements done with GC, then you have a shed on the side of the road, and then you have the personnel who will change the gas tanks as a carrier gas, and then this is the different logistical aspects that will give you, if you follow them right, then they will give you the good accuracy. If the person who is in charge goes on vacation and the other person in that month or 2 months or whatever is forgetting some steps, then your error bars are different, and you pay attention to all these workflow things. Okay, so mathematically, and we were discussing that those analytical instruments, the classical analytical instruments, they're first order or second order devices compared to the so-called zero order sensors with one output, because when the sensor has one output, it will change its response to something. It can be a gas concentration, it can be aging, it can be poisoning, it can be, well, it's an infrared sensor and the window is dirty, it will change the signal, and I don't know why. Okay, so the first order devices, they have the on purpose independent variable, and it should be selected wisely in such a way that if you have such an independent variable, then you will have different signatures or patterns or other type of synonyms of how these different analytes look like. Okay, and example at the bottom is that this is infrared spectra of different types of volatiles, and in order to understand what is what, you are calibrating in the knowing what type of volatile you have, and then also if you are expecting different interferences, you must calibrate for those interferences as well, so you can know what is the signature for those interferences. If you have two independent variables, then it's a second order device, and now you can see that you differentiate those responses into two dimensions, and an example from GCGC shows that that's how they may look like, and mathematically you don't need to calibrate for unknown interferences at all. So that's mathematical rule that is very useful to us. Okay, so from the sensor perspective, we see, okay, so what independent variable we can induce, okay? And maybe one independent variable or two or more or whatever, but it really will help you to see what is behind one plane of the single response, because if I will have the right independent variable, I can have the most famous painting, okay? Or if I choose the wrong one, then I will not have the improvement in my performance. So choosing the right one is very important. So I will show you a nice example of initial results in that, and those will be, you may expect, there will be the different sensors in the sensor arrays, okay, sensor arrays. But traditionally in gas sensing, the data is presented with this and maybe some other ones, but these are the most popular. So the principal components analysis scores plots. These are each data point is a result of different orthogonal transforms of raw responses. And if you see the different direction for one gas, like hydrogen and acetylene for another direction, and methane for another direction, if you see that, that's good. If you see that binary ternary mixtures are in the middle, it's also good. If you don't see that and everything is collapsing, that means whatever the sensor I had is not good enough for those gases. So I need to do something. So that's a very straightforward visualization that is used for more than 90% in cases of all kinds of commercial devices as well, and in addition to different research papers. So another methodology to show the differentiation is hierarchical cluster analysis, where you can see that in this example, all these gases are clustered by color, so nobody is mixing. And these clusters are separated with horizontal lines, so the longer the line, the more distance is from one cluster to another cluster. The third example on this slide is confusion matrix, where you are predicting some gas from the measurements and you know what that gas was. I call it true gas, and then predicted gas. So if we're predicting in many replicates nicely and different concentrations and so forth, then you're predicting as many times as the cells in the diagonal line show you. If you are outside of this diagonal line and you're not zero but some number, that means that you're predicting wrong way, this many times the wrong gas. So that's the ideal confusion matrix, where there will be no numbers except of zeros on non-diagonal cells in this table. Okay, so we mentioned the gas sensors, gas sensor arrays, and in more than 40 years ago, it was shown that if you combine several sensors that are broadly responding to different gases into array, and you look at the response together and apply some data analytics from the previous slide, then you can differentiate between those different gases. Nice examples following this 3-sensor array include more than 300 sensors, 10,000 sensors, 65,000 sensors, 1 million sensors. Just stop. Okay, so that's very nice examples. Now, I'll show you that in literature, I have many slides, but I'm choosing here to show that you can differentiate 8 volatiles and 15 and 22. These are different nice research papers. You can differentiate 24, you can differentiate 30 plus. And the reason that I'm showing this slide from Nate Lewis' work is from Caltech from 1996, is that he was showing that if you are choosing the different sensing elements, okay, and different gases and stuff, then you can have up to 5 dimensions in your response. So the more dimensions you have, the more differentiation between gases you have, and you can differentiate between mixture individual things in the mixture components. So the more dimensionality you have, the better. Okay, so this slide is showing the kind of some quotes from every review that I saw. Okay, and the latest reviews are saying, well, drift is a problem and we need to focus on it. And 5 years ago, drift was a problem. 10 years ago, drift was a problem. This sensor array field is 40 years young. Okay, so the reason that it is not a solved thing, okay, I'm calling it tremendous challenge. I'm not saying showstopper. I'm just calling it tremendous challenge, because when I'm a fresh sensor and I'm calibrated, then my prediction errors, I just calibrated it, are small, okay, or 0. And then under the uncontrolled conditions, when it is out of my hood and so on, then individual sensor elements start to drift differently, okay, that's why. And when they are doing this independently, then the more sensors I have in the array, the more total error in my prediction things will be, okay? And that's how things are going these days, and that's as a community we're focusing on what to do, okay? So what to do. Now, we need to remember this Mona Lisa image. Why? Because that image says, I'm independent variable. I'm not sensor array element. Just think outside of the box, because you are in the box for 42 years. So if we look at this slide again, okay? So I'm saying that, okay, think what can be the sensing material that has more than one response mechanism. Maybe I will swell and change the resistance because I'm a ligand functionalized nanoparticle. Or maybe I'm conjugated polymer like penny or whatever that will change resistance, and it will swell and it will change color and this and that. Maybe I'm some more or some other thing that may have multiple response mechanisms, okay? So that's one important aspect for the sensing material itself. Another very important aspect is what type of independent variables we can induce, okay? And nice examples in electrical transduction principles sensors is that you can modulate temperature. It was shown for 30 years, okay? What's wrong with that? Nothing. You can modulate the bias if you are electrochemical sensor, okay? You can modulate the power if you are a ref resonator. You do multi-frequency impedance measurements, things like that. For mechanical sensors, you can also modulate power if you are a resonator like this SAW or others. You can look at multiple harmonics, also look at impedance responses. If you are optical sensor, like our bi-inspired things, then you can look at the spectral content. These photos are from my previous slide. They are not boring, but we apply more things to them rather than I'm measuring resistance. That's what I was doing, okay? So that's a very important aspect to think what can be wisely applied for expanding the dimensionality. And I'll show you the examples of what can be done. So these are some examples of vapor response mechanisms in different sensing materials, as I was describing: conjugated polymers, monolayer protected particles, stuff like that. Okay, so in literature you can see nice examples of vaccines and 2D materials and grain boundary reach and so forth. So they're very inspirational to see how they can help me, rather than, okay, nice paper, and let's move on. So because more and more projects are about more and more challenging asks, and we need to come up with the solutions to solve those asks. So this slide shows there are different new innovative physical transducers with multi-response outputs, like multi-harmonic resonators, as mentioned, acoustic, electric, mechanical transducers, combination of quantum and electrochemical capacitance, and chemoresistive potentiometric readouts. So these are nice examples, and we can think, is it good enough? What can we add more? What can we add in addition to transducer design, excitation conditions from the previous slide? So these are all the things that we as a community think about. Okay, so as our research center, our research teams that I'm directing, and we are thinking about what projects to work on and so on. So we work in the RF and microwave frequencies. You can see some examples of our wafers and stuff, and also in optical frequencies. And philosophically, we're focusing on our tricks across the electromagnetic spectrum for solutions, how to not to be afraid of complex chemical mix. And you remember these cartoons from some slides ago, but in this case, our detection solutions are more unobtrusive and more friendly for remote deployments and stuff like that. Okay. I didn't use the word AI yet, and I will not use. And the reason that I'm showing this slide is that there are many synonyms: chemometrics, multivariate statistics, machine learning, AI. Maybe some new will come soon, maybe not. But if we have the garbage in, it will be out, okay? And we need to define what it means. And in order to define, step one, perhaps, or must, is to understand how to do the measurements. So when I will save the file, I have 27 data acquisition laptops. So if I want to save a file, I want to save a file that is not garbage. And I need to know when it's garbage, so I will not click the save button. Okay? Because after I click the save button, I have PLS toolbox, all my people have machine learning toolbox, and we look at the file. Okay? And then we have not one, but maybe 3 or 4 team members from machine learning team who are looking at the same file with their perspective, because they're trained as mathematicians, chemometricians, and so on. So if that file is garbage, there is a lot of effort to look at my garbage. So I need to make sure that we save the files correctly or nicely, okay? So you can see many data analytic tools that are very popular, and we're developing the new ones to improve the stability, selectivity, and sensitivity. And these are some examples of that work. And it's I would say two-way street, because we are learning, or we are inspiring our machine learning team members to say, what should I do from the hardware? So their prediction things will be with small error bars. Just tell me, do I need to reduce noise by 10 times, or by 2 times, or by 1,000 times? Because if you say by 1,000 times, don't say it. Okay? If you say it by 2 times, I'll promise you I can do it. Right? So these are kind of things that we are really discussing. And overfitting or other type of crazy things, we are also prevented by having the right data sets. Okay, so two of my examples will be on RF sensing and optical sensing. From RF sensing perspective, this is a classic semiconducting material that was developed in 70s to save many lives. Okay, and to save many lives, you're detecting the high concentration of combustible gas. Good, and to do that, resistance readout is just good. Okay, it's good. It's doing the job. Okay, there is mechanism of what is happening, and you see the classical equivalent circuit from literature because it's the most popular. There are many more, but if you are to do more data extraction from what you want to achieve from that sensor, then what we showed is that if we do the impedance measurements at a particular frequency range, and we're calling it the electric excitation region, okay, because it's on the shoulder of the of that peak, then we discovered many interesting features. Okay, and right now we have only 15 granted patents about these many crazy features. Okay, and many other pending. And we are doing the data analytics on board, and we're using the very small off-the-shelf components. And this is an impedance analyzer from Analog Devices, and these are some other things. We have our own one. And the reason that it made to discover, not because I got them from DigiKey, it's because of the performance capabilities that we discovered. So if we look at the conventional resistance, then if we're increasing the concentration range of a gas like methane as an example, then because it's a power law response at the resistance, then we see more and more nonlinearity. So when we sit at different frequencies with our imaginary part of readout, you can see that the linearity is as shown here with these 16 steps of concentration changes, and it's as if I pasted them 4 times. Guess what? No, they were measured at different frequencies. Okay, so another example that with the resistance readout, the higher and higher humidity levels make the response to look like this, and then if we're doing our dielectric excitation readout in the imaginary part, then you can see that we are keeping our linearity, and we are not afraid of high humidity levels. Another example is where the environmental air temperature is changing, then we expect the resistance background or baseline will change, as you can see, if we're doing the measurements in our environmental chamber from 50 to -25 C. Okay, so the baseline change is expected, and also the sensitivity change is expected. You see at lower concentrations, the sensitivity is way different from the lower temperatures, is way different as compared to 50 degrees C. So this is the same experiment without any drift correction, the blue response, and you can see at particular frequency the temperature effect is not there, and we saw from physical sensors that that's because at that frequency you are compensating all kinds of temperature effects in your sensor system that has substrate, electrodes, sensing materials. So that's a temperature independent response over this temperature range. My other 2 examples about the drift correction and signal to noise improvement. So here I'm showing that if you sit at a particular second frequency that is on the tail of that response, and on purpose that frequency is selected where there is no sensor response to the gas, and it's only the tail or the baseline that wiggles as a function of what happens. And at both frequencies, this baseline change is the same, as you can see, and that's how we are easily correct using these two frequencies of the response. You can see that the accuracy is improving and the prediction error bars are also dropping quite nicely. So if I'm doing it with the resistance readout at these low concentrations, okay, then mathematically I don't see anything in this second dimension or first dimension. So that's a improvement just like that for free. So another improvement is that instead of looking at two frequencies, if you look at many frequencies, what you measure, then you can improve the baseline as I'm showing you here, but also you can improve the signal to noise as well. And that's something that was also counterintuitive to us, but we were happy to see that again and again. And that's another advantage of such a readout. Okay, another well-known advantage, I would say, and that's why these figures were in our supplementary information, is that if you look at the different frequencies of the response to different gases, then you can differentiate them by doing PCA or one versus all responses. And with modern microelectronics, I'm comparing here the response from a small impedance analyzer, integrated circuit one, that's in my Petri dish. I have many, okay, they're $5. And I have many of these, maybe a dozen, okay. But when we decided what to do, then we switched to the small impedance analyzers. But I'm showing you here that the signal noise and linearity and all these properties are the same. And that makes us very attractive use for unobtrusive applications like that. So I have a couple of more minutes. I will show you the examples of photonic sensors. And in optical gas sensing, there are two types of gas sensing. So one will be with organic dyes that will change fluorescence or color, and other one is based on the physical principles, okay, of light interaction. And when we look at the tropical iridescent butterflies under optical microscope or with GEM, then we can see that this iridescence comes from multilayer interference and from the diffraction on these nanostructures, okay? And for us, it was very interesting to do the initial gas measurements because it's the nanostructure that is open to air. And because the signals are relatively small, so we're looking at the differential reflectance mode where we're normalizing all the responses to the response in air. So you can see the three-dimensional PCA scores plot where we're differentiating between water and methanol and ethanol in this quite nice way. And I'm showing the raw spectra just to pay attention that some of the spectral features are very similar. And with the PCA, we're looking to differentiate when the spectral features have the differences. So we are either manually or automatically selecting only those spectral features because the resolution will be better. So in literature, it's nice to see that a lot of groups are following this nanostructure work, and you see detection of 10 vapors and mixtures and 5 vapors. But I'm highlighting this result, very nice result, because the dimensionality is also 5 dimensions, okay? So dispersion with the 5 PCs, and it's same to what we saw with the sensor array, okay? So we learned about the design rules on how those sensors operate in the room temperature, and we started to make the nanostructures I'm showing here, and also comparing the response with the traditional sensor arrays. And we're quite happy to see that we are outperforming the traditional sensor arrays. From the baseline correction perspective, I have some more time. Okay. From the baseline correction perspective, with conventional machine learning tools, and they can be PLS or SVM, anything that is coming from that previous slide, sometimes some slides ago. So if we are calibrating our response or training, there are those synonyms, okay? And then we're predicting the future. If that future contains some drift, I don't know what that future will have, and that's why I'm not ready, and that's my result, okay? So if I'm developing or if I'm using the new analytical tool or model to not to be afraid of those potential things, then you can see an example where I'm not afraid or I'm not affected by the drift. So that's another example in the optical sensors. So from the fabrication principle, we are working towards also more exotic sensor structures. As you can see, the high aspect ratio materials, and also quite exciting to see last year the press releases that metamaterial structures that used to be only in science articles and stuff. Now there are commercial products that are in metal lenses, because in this way they're flat and less heavy and stuff like that. Okay, so we also moved from room temperature applications to high temperature applications as well. High temperature for us is 300 C, and you can see examples of our nanoparticles that we are forming, either same material such as gold, they are catalytic materials, and these are of different sizes, or we're forming them with different types of noble metals as well for our catalytic readout. So I also have several ocean optics machines to do the spectral measurements, and the reason that I made this slide just to show that in the art of wearable sensors, there are solutions with not one, not two, but 3 LEDs for the pulse oximetry, because typically they use 2. But with the 3 wavelengths pulse oximeter, you can see the size and so forth. Then we're able to differentiate between our analyte gas and interferon in the same way as we're using the big light source and the spectrometer like that. So that's quite exciting. From biosensors perspective, I have a couple of slides just to show that the industry or the market is also not small. You can see these numbers, and these are some examples from commercial offerings: implanted sensors by this company, skin interface by this company, and then in Nature family journals, different things that somebody can swallow or have a tattoo. And most recently, I put this thing because I had that definition of who is a biosensor, okay? And I have a paper, no, it's not my paper. I have a paper in Nature Communications, and I'm calling it a biosensor. What's your problem? Okay, so we need to keep in mind these terminology things, and when we talk to our collaborators, it's very important to be on the same page, okay? So my example here is bioreceptors, and the reason that we're using aptamers is because they are as good or maybe better as compared to antibodies. And better means that I don't need to store them at foresee. I don't need to have a special animal to grow them. Sorry, I don't. Okay, no goats, no cows, no sheep, I guess. Okay, sorry, but also there are many other features, and we did the first biosensor, and that was very interesting, and then we grow into different other areas. The most recently, I'll show you the example. The most recently, we were doing the detection of individual COVID-19 virus particles, okay, with our NIH program, and develop the integrated circuit ourselves and build it as well for our readout. So that wafer that you saw in one of those slides on the left, so that was a wafer of these guys. Okay, so you remember this bar graph? They're awesome. They say, hey, don't expect that I will respond only to that. Okay, and this bar graph shows that, yeah, if I'm a bioreceptor such as aptamer, look at me, I'm responding only to what I'm designed for. Why? Because okay? And these are the different interaction forces and stuff like that, okay? Now, of course, it's irreversible. It's a very strong interaction. What's your problem? Not a problem, but, well, so in addition to those bullets of modulation tricks or excitation conditions, so this slide shows the chemical deactivation or chemical modulation, where on purpose you can say, hey, I am immobilized epitomer layer, and if I will apply some modulation thing, then I will make that layer reversible. And an example here is chemical deactivation. People show optical deactivation, thermal one, and stuff like that. So it's something to keep in mind, and there are many reasons for doing that, okay? And this is an example. This is our DHS project some time ago. And for fun, we showed that, yeah, we can do 365 bind release cycles. And look at me, my KD didn't change, okay? So I'm still alive, I feel good, and I'm as strong as I was in the beginning. So that's a very exciting thing for us. So if I will conclude, and I have the how we're scavenging water from air and doing the chemical deactivation with deionized water and stuff like that. But I would say the expected benefits will be that there are different methodologies for multi-gas differentiation, and for years or for decades, there were some examples in literature how to do that, okay? And unexpected ones are benefits for drift correction, for signal noise improvement, also eliminating the different types of ambient effects. I showed temperature and humidity as examples. And also you saw ideas on how to implement those things into biosensing as well. I also want to add that, say, for the temperature modulation, I have a slide note here that shows not one, but 8 different sensing elements from different companies that say, hey, we're doing it. And they look the same. Okay, so that's how it looks like. And I think that's my thank you slide, and thank you guys for your attention, please.
Thank you so much, Radislav, for this very, very nice talk. Amazing. I don't know how many questions, but I will ask the audience. Please, do you have any questions? We can start. Any question?
A lot of questions.
A lot of questions. Please start, Anisha.
One of the things that I wanted to know is when you were showing all the devices, it was very interesting because you went from the idea conception stage to making a small, less than a coin's size device. So I wanted to know, when you're starting off with an idea, what are the things that you keep in mind so that 2 years, 3 years, 5 years down the line, you can reach that small stage? And as early career researchers, what kind of ideas should we start developing so that we can think along those lines?
Yeah, it's a nice big question. Yes, thank you. So step one, I need to have that idea clearly in my head first, okay? And clearly, I don't know what's the definition. Is it a sentence or a paragraph or 2 pages? Probably it's a couple of sentences, okay, in my head. Step two is I'm practicing those sentences on people that I respect their opinion, okay? Why? Because, and like small startups, my daughter was in 2 startups, and then all of them didn't make it. So now she's with Google. Oops, why? I don't know. But so if that idea doesn't resonate with those communities, then I polish my idea. Okay? So that's a step 2. I would say step 3 is to see how that idea can be phase in what you're gonna do this week,
Okay.
or by Monday,
Okay.
or by lunchtime, or this year, or so what type of things you think you would like to accomplish, and because this idea is fresh, new, crazy, then you kind of decide once you achieve something, roughly what you're gonna do after that. Okay, so that's, I think, how it can progress. Okay, another important thing is that you remember my two Gaussian curves.
Yes, yes.
Yeah, I like that. I like that you like that. So in the beginning, if I didn't ask many people, okay, and it still at the end resonated with, you know, those covers, whatever, it means that I somehow asked those people anyway. Okay, so trying to see what is the unmet need for those sensors. So once that idea become a reality, such as nice plot or 5 plots or 10 plots, okay, supplementary figures and stuff, then who will get excited because those plots are really exciting, okay? And so that's how I think it can be structured. So time-wise and opinions and kind of specifications that are rough, okay? And you need to try to kind of not only to listen, but to also ask, if possible, why those people are saying that they need this and this and these things, okay? Because maybe often, not always, maybe they don't know exactly what they want, and talking to people like us make them not sharper, but more polished or more kind of deciding.
Okay.
Make sense?
Yes, yes. Thank you.
Another question, please? Maybe I don't know. Shreyas, do you want to ask question?
Yeah, I'll take that.
Yeah, I think.
When you describe the correlation between our biosensor response and the general biomolecular tests like PCR, ELISA, do you think that we need this kind of graph, or we need also, I don't know, maybe the development or of a rock card with controls and partials for real samples?
Right. So depending to whom you would like to impress,
Okay.
okay? So if those people understand what the health rock curve is,
Mhm.
and that's the only thing they like,
Okay.
you impress them with rock curves.
Okay.
But you're not doing it in your first week of
No.
project.
No.
Right. So you're getting ready to do those measurements
Mhm.
because it will require a lot of things to happen, okay? And before that, you are, you know, making sure that when rock curve time comes,
Mhm.
there are no surprises that you say, oh, I wish I did this. So it's kind of a lot of earlier work, which is super impactful. Yeah.
And
Mhm.
also, do you think that it's better to test our biosensor for our target with in real samples such as complex matrix with biofluids, or we can test it before with cultures or other like analogs?
So what's your answer?
For me, it's before with the analogs and then with the real samples.
Good then. Okay, now, so when I did the invited talks with biosensor people around the world, it was, you know, people who are doing the biosensing with SPR and Rick Van Dyne when he was alive, and other people all of them confessed at the end of the talk or in the beginning or whatever that in real sample, okay, the signal to noise, some of them said 10 times, some of them said 100 times, some of them said 1,000 times more ugly, okay? And well, it's nice data points, okay? So I always look at the bright side. So the bright side is that sometimes it was 10, sometimes it was 1,000, and we had examples where on purpose we designed our aptamers with a conformational change and rather than electrostatic interactions, so they will not be affected by crazy things that will affect the electrostatic interactions, okay? So it's a kind of thinking what can happen. So, but maybe you will have in your examples next time when you will be invited speaker, where you say, we have no loss of signal to noise. This is my real sample, and this is my synthetic one. Look, that's why you are, keynote speaker. But I think if things are well thought and well kind of understood how to fight for that, and if ELISA or whoever else they are designed not to be affected, then what we can learn, right?
Thank you, Krista. Others, maybe you have questions? Nicolas, you have questions?
Yes, maybe I want to clarify your point because I'm not sure to understand. It's the way you tackle the drifts. Maybe slide 40 is you use a different type of interrogation for the sensors, and that's tackle the drift, or is it by the algorithm of IA, of machine learning, that you may have this effect?
No, only hardware and brain, human brain. Because if my signal is garbage, machine learning will not help me. Okay? Because look, if I by design will not measure here, okay, then there is nothing to save you for the drift reduction. Okay? So again, all our team members have machine learning toolboxes. Why? Because I want them to have. We have not one, but sometimes, as I said, 3 or 4 people from true machine learning team to help all together. Okay? So step 1 is to have the relevant data set that is captured. Because what I learned is in machine learning community, when they get the file, it's like a Bible. Zero noise. Why you are smiling? It's a Bible. Zero drift. It's ideal. Okay? And then they, work on that. And what we want to understand is how can we work together so if something can be improved, tell me. Okay? So it's a two-way street, and we use it all the time, as you can see. But and you can see it with your PCA tricks, is that if you use the whole spectrum and some spectral features are just noise, then it doesn't help. But the pain is that it doesn't tell me that, hey, get rid of them. So either I know as a human learning that I need to use additional pre-processing, or you see visually that these are the spectral features that are more relevant, and then you use them. So it's really different ways of getting the best out of that file that you say, or I say. Make sense?
Yes.
So it's in future, everything will, there is a scientific novel where the scientists like me and you in future, all we do is we look on internet because all the answers are there. It's a science fiction novel, but it was written, 50 years ago. But right now, it's something that we need labels for machine learning. We need this. We need kind of guidance because I showed the list of tools. Okay, I have another slide with 3 columns with a very small font of many other tools. Okay, so I think without, if it is unsupervised search for the best tool, I don't know if you want to do it. Okay, because I don't want to do it. Because it will be nice local thing, which will be matched only to the file that I provided. So it will be not general. So it's a complicated question. You agree?
So, sorry, I'll just continue along that question. So, are you suggesting that if we use physics-derived features, like if you have for example, a resonance spectra and you're looking at the magnitude, the frequency, the quality factor, things that we can explain with physics and then use these to train our models, we would have more explainable models that we can understand what it's doing and then we can
Right.
reduce the misinformation and interference.
Right. So probably even 3 or 5 years ago, or maybe 2 years ago, explainable or physics constrained or physics inspired or whatever, AI was not a term that people used.
Yes.
Why? And for many years, without that physics thing, there were some success stories, but more and more customers are coming to me and they're saying, I spent 18 months and many millions of dollars. And now I'm stuck because I don't have the result. So that constraint that based on reality is something that must be added. And if it is added automatically or with the supervision, it doesn't matter.
Okay.
And if you do that, then you will have more impactful stories to tell.
Yes.
Okay? Because you will be the first. And then when I look at the papers published by those Nobel laureate people in chemistry in Nature, all of them have the word robust in the title, robust, and none of them have the word AI.
Yes.
Why? Because robust wins. So that's very inspiring to me. Yeah. And we are doing exactly what you're saying. Yeah.
I think we have all of us many questions. Me, I think this afternoon I come back to your presentation. There is many slides that really are interesting, but I have one precise question, Radislav. We saw here that there is many kinds of technologies are already existing, are already efficient, selective. But when we want to buy from, to some solution commercialize it, we find really good physics sensors, means pressure, temperature, and all that. But chemicals, gas sensing, I bought MEMS that the price is not $1, it's $50. And they are not selective because we bought them, they said that they can detect that. When I try to use them using the robust generator of vapor, I know really what I am sending. I try them. The response is not really accurate and robust. My question is that why many years ago we are speaking about devices, quartz balance, we can see a very nice paper you show an array of quartz balances, but we cannot find them to buy them. Why? Question.
So eNose reports, and I'm the North American chair of eNose people. So I love this dimension and I like everybody. So chemical review articles and others, they have nice reviews. In 2008, there were a review on eNoses, good, and there was a humongous table on 4 or 5 pages of different companies. I'm eNose. I'm eNose. Good. So little by little in other review articles, the table gets smaller and smaller. Okay? So my personal opinion, and that's why I made that bunch of quotes, is that when it drifts, at least now, there is still no solution, and in my opinion, we need to focus on something to be famous, okay, or to graduate, okay? So, now, when I look at different multi-sensor systems, from multi-ray and stuff, they're smart people. They're in the business for decades. Do they combine responses? The answer is you know. Okay, you made this face because they do not.
Yes.
Okay, why? Because they're afraid, and not afraid, but they want to sell those widgets, and they sell them, and that's why they don't combine. Because if something drifts, okay, the other one doesn't. So they don't combine, okay? So there are, I have in some of my tutorials, I have a table with 4 companies that are around, okay? So they're startups and stuff like that. So it's fun to watch.
Okay. So maybe,
So my observation is that stability, if stability is not good enough, then returning customers will not happen, okay? And we used to have GE Plastics in Cartagena and in other places and stuff, and they were developing all kinds of materials and for automotive applications and stuff, and they were measuring the smell of a new car, because new car smells in a nice way. And they were saying, well, we bought this electronic nose, $40,000. Do you want it? I can send it to you for free from Europe. It's so ugly. I don't want it. But you're an electronic nose person. Maybe you will use it. You're my friend. I said, okay. So, but I'm their friend, but so we need to, that's why I had that slide with the quotes. Okay?
yes.
And the markets for total volatile compounds. So it's a theme, but if that market doesn't grow, then those sensors become $50 per sensor or 100, or they
Yes.
stop making them because only one person bought one sensor.
Yes.
Good for you, thank you. Right? And then why should they be made? Okay, and for example, Sensirion, they stopped making, no, Alpha Sense people. So they stopped making the metal oxide semiconducting sensors and stuff like that. So they were designed for detection of high concentrations
Yes.
before. So if we're trying to detect smaller and smaller, it's okay. It's my choice.
Thank you. And another question, still we need a GC to calibrate all of these kind of sensors. No?
Okay, I will describe, but then the thermal modulation thing that I showed was that I said there are not 1 but 8 examples on one of my slides. Okay, I can add them, or I showed them in some tutorial. Andreas Schulze and other people and Wolfgang Gopel before, so they were showing that we can do more multi-gas resolution. We know that. But also people show that you can improve stability, okay? And you can improve sensitivity by doing the right things with your metal oxide material, okay? So we're adding another dimension with our frequency readout and stuff. So, but these are very useful encouragements and examples from what has been done, and modulation was known for more than 30 years. So it's a lot of nice work. So sensitivity, stability, and multi-gas resolution, selectivity. So these are the things that were shown. Yeah.
So thank you. So let's take again. I think this is the end of the
Yeah,
talk.
thank you,
So
guys.
yeah, thank you.
Mhm.